A mental stumbling block for many users of SEEP-W when they first start using SEEP-W is the concern as to how do I get my conductivity function and how do I get my volumetric water content function. I'm going to make a few brief comments here that it is not all that difficult, but right at the start let me note that there are many cases that a good approximation of the volumetric water content function is generally adequate for the problem. Now, there are cases, it is true, that we need to define the volumetric water content function and conductivity function very carefully, and we will see examples of this at the end of the next SEEP-W session. But in many cases, particularly steady-state cases and flow-through embankments and so forth, an estimate of the volumetric water content function and the conductivity function is more than adequate. So a few comments then about how to define these functions. Number one, SEEP-W includes some sample functions. We have included with the software some functions ranging from clay up to gravel. So this is the clay and this is the gravel. And in many cases these sample functions are adequate for a particular problem. The other thing is that recall that in a volumetric water content function, we already know the saturated water content. This is the porosity. A value not difficult to determine for a soil sample. This is the air entry value. And it is related to the size of the capillary zone. And for most soils, you probably have some intuition as to an appropriate height of a capillary zone. Clearly for a gravel, the capillary zone is probably very shallow, not very high, and as a result the air entry value is quite low. For a clay silt, the capillary zone may be in fact be a meter or 2 or even 3 meters, and as a result the air entry value can be much higher. My point is that determining this second point on the curve can be related to your general understanding of soil behavior and your field observation. The third point is that the residual water content is not that clearly defined sometimes, but even if you were to make that the phi residual is approximately 10% of the saturated water content, it's not an unrealistic estimate. The one thing that is more difficult to define and have an intuitive feel for is the slope of this curve. And as I have noted earlier in the SEEP-W presentation, this slope is related to grain size particle distribution and to pore sizes in essence. And as you can see from this illustration here, clearly that a clay, there is a wider distribution of pore sizes, and so the slope is lower. Whereas in gravel there is probably more just one pore size, and as a result the slope is much steeper. So it is not that difficult to think about the volumetric water content in terms of those 4 ideas. Nonetheless, SEEP-W gives you these sample functions, which gives you a starting point as to the approximate shape and the range for a variety of soil types. So this is always a good starting point if you don't have any other data. Now, in almost 100% of the cases, the conductivity function, the K function, is determined from the volumetric water content function. At the start of SEEP W session 1, we noted that the hydraulic conductivity function takes its shape from the volumetric water content function. And as a result, we always first estimate the volumetric water content function, and we could use a sample function, for example, and then once we know we have selected a volumetric water content function, then we could select and estimate the hydraulic conductivity function, as we did with our example earlier on with flow through a dam. So we selected a volumetric water content function, we selected an estimation method, we specified the saturated hydraulic conductivity, and we estimated the saturated water content, and we were able to estimate a conductivity function. Let me repeat that in almost all cases, the hydraulic conductivity function is never measured. There are special cases where it can be measured, but in all practical cases, we always estimate the conductivity from the volumetric water content function. So in a steady state analysis, we don't need the volumetric water content function, but we often set one just in order to estimate the required conductivity function. So, starting with a sample function for volumetric water content, and then from the volumetric water content, we estimate the conductivity function where we specify the saturated hydraulic conductivity. Now, it is possible to estimate the volumetric water content function from grain size, and this is available in SEEP W. You can select an estimation type that's called grain size data, and we can then estimate the volumetric water content function, and we then need to specify the porosity or the saturated water content, and then we specify the diameter in millimeters of the 10% passing and the 60% passing, and we specify a liquid limit here, and from that we can estimate the volumetric water content function, and then once we know the volumetric water content function, we once again can estimate the conductivity function. Now, I would say that the estimation of the volumetric water content function from grain size only works well for fine sands or silty sands. It does not work well for clayey soils and should not be used for clayey soils for that reason. It is also possible in certain cases on special projects to measure the volumetric water content in the laboratory. And it is not all that difficult to do, as we'll see in the next slide. So first of all, we measure the volumetric water content, and again we estimate the conductivity function from the volumetric water content function. Here is a simple apparatus that is often used. It is known as a Tempi-cell, and these are quite common. They originated from agronomists and soil scientists. And here is a picture that was taken from the soil moisture soil measurement systems website. And basically, this this apparatus is set on a scale, and air pressure is applied to the sample. And the air pressure comes to equilibrium with the suction, and as a result some water drains out of the sample, and the apparatus is continually weighed, and as a result it's possible to measure the volumetric water content function. So here's two suppliers, Soil Measurement Systems in Arizona, Soil Moisture Equipment Corporation in California. They market these types of cells. And in actual fact, we are now aware that there are quite a few consulting firms now offer this service commercially in their commercial labs. So it is possible to measure the volumetric water content function, but this is something that is only done once a lot of preliminary analyses have been done and it's proven that the volumetric water content function for that particular site or conditions needs to be defined with considerable care. So this is possible. Let me repeat, though, that measuring the conductivity function is seldom, if ever, done. Now, it is also possible to estimate the volumetric water content from parameters. These are published parameters, and as a result, with the Fredlin-Zing function, if you can define A, N, M, and the saturated water content, then you can estimate a function. And these parameters are often published, and you can get them from publications. The same thing with the Van Genooten parameters. You specify these parameters, and these are parameterized functions, and you can estimate the volumetric water content function from these published parameters. Often quite convenient if somebody has made some measurements and published these parameters. In summary then, as we have noted several times already, always start with the volumetric water content function and then estimate the conductivity function. It is important, however, that when the conductivity function comes from the volumetric function, or if you happen to create the conductivity function independent of the volumetric water content function, for good results, the air entry value should be the same for corresponding functions. In other words, the volumetric water content function and the conductivity function should have approximately the same air entry value. This brings us to the end of our SEEP-W session 1, where we have concentrated on steady state analyses and have introduced to you the three main components of a steady state finite element analysis. Number 1 is geometry, number 2 is material properties, and number 3 is boundary conditions. And we have demonstrated to you some special analyses like a plan view analysis, axisymmetric analysis, and so forth. But this brings us to the end then of SEEP-W session 1 on steady state analyses.